This video is a summary or the highlights of Chapter 3. And in Chapter 3, what you explored and hopefully learned was the physics model for constant velocity. So the equations we have, the graphs that you learned to read and interpret are all, they together comprise what we call the constant velocity model. I probably should put constant velocity motion model. So this equation should look familiar. You've played with this. A graph like this should be easy for you. Frankly, you should be able to describe what's happening in this graph, how it relates to you should be able to see the equation in the graph and be able to describe the motion depicted by a graph like this. So we're going to review that very quickly. But where we're going to end up is the following. I mean, actually, the main, one of the most important ideas, not the only idea, but one of the main, the last things that we visit in Chapter 3 is the idea of position time graphs or motion graphs. That includes velocity time, which we'll explore. Can't emphasize this enough. This has to be very well understood. Slope of a position time graph, xt, corresponds to the value of the velocity time graph. That's one of the endpoints we have. The other endpoint is we're going to use as a segue into Chapter 4. It's not going to be the first thing we study in Chapter 4, but it's an important idea that will make, if you can see it in the context of Chapter 3, it's going to be much easier to see it in the context of Chapter 4. In the same way that in Chapter 3 we have an equation for velocity or average velocity, we're going to look at a different type of motion in Chapter 4, one that you're familiar with any life experience. It's going to make sense to you to describe that motion, but the math might be new. And we're going to build the same kinds of models for that new kind of motion, just like we did with Chapter 3. So the tools that we use in Chapter 3, we're going to use again in Chapter 4, but for more complicated motion. So just to point out the most important things that should be comfortable. So if I say something that makes you go, I'm not sure what that is, that's the reason to come to academic support, okay? The equation should be pretty straightforward. Important point now. The fact that whether you write t or delta t here, you're really talking about a time interval. A time interval is best understood, or should be understood, as the difference between two clock readings. Right? So if I'm, in this example, if I start at time equals 0, I don't know what time, maybe it's 11 o'clock in the morning or something, who knows. But at some point, I have basically a stopwatch, and I start it. And at time equals 0, I'm at a certain location, x naught. At a later time, t1, I'm at a different location or position, x1. Sometime later, at t2, I'm at a different location, x2. This part of the journey, this middle part, from t1 to t2, I can apply this equation to that, but notice that my delta t, which is this amount of time represented on the graph, numerically, that's, if I have the same stopwatch and it's been running this whole time, that delta t can be calculated for this part of the journey as t final minus t initial, or, again, for this part, this time interval right here, let's just call that t1, 2. So for the time that elapsed from t1 to t2, that's got to equal t2 minus t1. So if this is 45 seconds, this is 30 seconds, and I want to figure out my velocity from here to here, I have to use the difference between the two time readings. Okay? All right. So I want to use this graph, this part of the graph, to emphasize that time, even though sometimes we put, it's just t, it always represents a time interval. Most of the time, it's trivial because we control the stopwatch. We could say, well, the motion started at time equals 0. So that's why it's sometimes convenient to just write t. Because if time equals 0, what's my final time? 15 seconds. What's the delta t? 15 minus 0. See how as humans we fall into the habit of just saying, just put 15. But final caution, don't forget that it's actually the difference between two time readings. Oftentimes the first one's 0. Okay, other things to get out of this graph. Some reminders. This is the equation. These two, the delta x and the delta t, have to correspond, right? So the change in position for the matching change in time, and vice versa. So over here, notice that I call this motion, this equation, constant velocity. So my velocity does not change. This number doesn't change. Wait a minute. Look at the graph, Mr. Cacchio. I see definitely different velocities here if I've understood everything I've studied so far. Why is that? Well, between t1 and t2, I have a certain slope. I'll call that v1. The slope of the graph is v1. Over here, I have a different slope. I'll call that v2. And you'll notice that, I'm going to write this out. You should hopefully make sense to you. v1, I have to use a time interval that corresponds to a change in position. Well, I've got x1 and x0. So that's from here to here, my later or my last position, final, is x1. That's minus x0 or x0. That's equal to t1 minus 0. So that's a velocity. That velocity could be very different from v2, which is the velocity from x2 to x1 during what time interval? t2 minus t1. And you could rightly say, Mr. Cacchio, why is this the constant velocity model? Well, that equation only applies when my velocity is constant. Wait, how do I know my velocity is constant? Let's suppose if you had a graph like this. Well, because in a graph, we plot the x values on the vertical axis, the time values on the horizontal axis. That way, this calculation is mathematically identical to the slope of the line from when to when, from 0 to t1. So there's a slope, v1, from there to there. It's constant velocity because we almost presume, or the only thing it could tell us, is the slope of that line from x0 to x1. Okay? If my velocity is not constant, then can I really draw this as a line? For chapter 3, that's the constraint for the model. That's the restriction. The presumption is I have constant velocity motion for some amount of time. So that's what allows me to say, well, if my velocity is constant, if this number is constant, then the slope of the line must be constant, and you end up with either a positive slope or a negative slope, and of a certain size or magnitude. Okay? Again, this should all be reviewed. Where does that leave us at chapter 3? Besides the equation, right, the other thing you experienced in chapter 3 were what I call multi-legged journeys. So you saw graphs where my position time changed, and I actually have different velocities. So I just want to make sure that was clear. Even though we call this a constant velocity model, for a whole journey, we might experience different velocities, but within different time segments of that journey, we have constant velocities. So that's why this model can still represent a motion where velocities are constant excuse me, throughout or during different time segments. But I can have my whole journey can still be made up of different velocities. So the main takeaway here, besides the equation, we should make sure we're comfortable with using the equation. The new representation that you practice is position time graphs and velocity time graphs. In fact, we'll do one for this in just a sec. We know that the slope of position time, of a position time graph, corresponds to the value of Vt. The steepness of the slope, or absolute value of the slope. So if I say slope and you're thinking a number, hopefully your math background reminds you that your slope can be positive or negative. So the absolute value of that slope corresponds to the magnitude of your velocity or your velocity time graph, right? So that's the magnitude or the speed, actually, right? Which is, if I've got a velocity, the size of my velocity, how fast I'm going and disregarding direction, that tells me my speed. The sign of your slope. So every slope on your VT graph has a sign. I have a positive slope here, I have a negative slope here. The sign of your slope corresponds to the direction of motion. Okay, am I moving to the left or to the right? Positive or negative? Positive position values or negative position values? Okay, or positive velocity values, negative velocity values. So let's take a look at this and apply it to, since I mentioned a VT graph, let's make one here. Without actual numbers, those equations that I erased would give you the number, right, if you knew all of these numbers. But I can tell you the shape of my velocity time graph very easily using what I wrote above or over there. So you also saw that when you did the lab, SparkView can read out velocity values. So if we look at velocity as a function of time, so this is meters per second, what is my velocity from 0 to t1? Is it, let's look at this, is if I have two, right, which one's steeper, this one or this one? Well, V1 is more shallow. V2 is really steep. So I would expect V2 to have a bigger magnitude. Also, V1's positive. So when we talk about the slope of xt being the value of Vt, value means a thing, a number along the vertical axis. So the value, the slope of this is the value of this. So whatever that V1 calculation gave, let's say it was V1, it would be a positive number because my slope's positive, and it doesn't change. The slope anywhere from 0 to t1 is the same number. Hopefully you'll see that you're good with that. If not, let me know. But that means I could draw my VT graph as follows. My velocity is constant all the way through t1. From t1 to t2, my slope is, what's the steeper? Is it steeper or shallower, right, than V1? It's actually steeper. So it's going to be a bigger value. Also, is it positive or negative? It's negative. So I need a bigger value than V1. So V1 is only this high. Oh, and it's negative. So you have to be negative and bigger than V1. V1 is like from here to here, so that's in the negative direction, that's from here to here. V2's got to be bigger than that. So V2 as a magnitude, right? The absolute value of V2 is bigger than the absolute value of V1. And it's negative, but it's also constant, and it does that from T1 to T2. So I have a velocity that does this now. And then over here, after T2, what's my slope? It's 0. So I'm somewhere in here. Okay? So that's a VT graph. So in the constant velocity model, you should, it models, or it can depict this kind of motion in terms of position and time, and this kind of motion in terms of velocity time. So your velocity time graphs in a constant velocity model, all your velocities are constant for a certain time interval, for a corresponding time interval. But if you look at the whole journey that is within scope for this model, I can talk about this entire journey if I just can break it up into discrete constant velocity time intervals. Okay, that model works. Okay, now we're going to end with something slightly new, possibly, is now that we're equipped with another kind of graph, a VT graph. right? VT graph. We can talk about graph characteristics. One of them is slope. So when I say graph characteristic, I'm not talking about a physics property. I'm talking about a characteristic of just the graph as a tool, as a thing. Every graph has a slope. If it's an xt graph, then the slope has a certain meaning. But every graph has a slope. Turns out that every graph also has an area. You met this way back when, very briefly, in a positive physics exercise, and at that time I didn't emphasize it, but now we're going to come back to it. The area under a graph is basically the area between the horizontal axis and the graph itself. It can be negative because the graph can have negative values. So the area from 0 to t1, so side conversation, we'll summarize things here. But if we look at area under a graph, we're going to use this as an example. From 0 to t1, the area of that graph is the area between this horizontal line and the time axis. Well, luckily, if you look at the shape, it's just a rectangle. So the area of that is equal to base times height of that shape. And the base is t1, and the height is v1. Okay, what about from t2 to t1? I'll call this area 1. T2 to T1, I'll call this area 1, 2, just to be clear that I'm going from 1 to 2. That area is also a rectangle. So let me move this T1 over. That rectangle, area under the graph for T1 to T2, I know it's the under part should be in quotes because this looks like it's above the graph, but whenever we say area under, we really mean area between, right? Between the horizontal axis and this graph, which happens to be constant. Because it's constant, I get a rectangular or square shape, and I get area is equal to base times height. What's my base? It's actually T2 minus T1. What's my height? It's actually V2. And remember, V2 can be negative. Area, we use area to help us remember, or it's an analogy, maybe a metaphor, but we do not think of area as a physical space, right? We don't, in the physical world, we don't think of negative area. In the math world, we can have a negative area in terms of these graphs. So we don't, I'm making it clear that it can be negative. It is negative. So if you have numbers, you keep the negative, okay? That's the calculation part. How do you calculate the area? Well, hopefully that's trivial, so I'm not going to spend any more time on that. The real question is, what did I just calculate? Well, if you look at the equations real quick, I've got time times velocity. Wait. Time times velocity. We know that a velocity is equal to delta x over delta t. If I multiply both sides by time, or time interval, I get my displacement. You practice solving for distance, for example, if you knew velocity, the amount of time. Well, if you represented that journey graphically, you would have something like this part from 0 to t1, right? I knew how long I traveled, and I knew how fast I was going. I even know velocity, not just speed. If I had velocity and it's positive, I could tell you that my delta x is the product of that, and the sign matters. I could tell you that my change in position was positive, so I got farther away from origin. Okay? Pretty straightforward? If it is, we figured it out. What's the area under a VT graph represent then? It actually represents delta x. Notice, slope tells you a value on a graph. Area does not tell you a value on a graph. It tells you how much the values in that graph changed. Warning, this is not a graph. Right? So some students, their brains want to see structure. So if the slope gives a graph, it would, some students incorrectly, so if you're taking notes, don't copy this down. Some students, their brains want or believe in the symmetry of things, which is okay. But in this case, your symmetry brain might want to see this. It doesn't give you an XT graph. You don't get that information. What you get is how much the position changed. So the closest you would get, it's kind of in between, right? Because if I had area under my VT graph, so let's suppose I calculate the area, let's say from 1 to 2, and I find out it's negative 20. If you look at the units, I should get negative 20 meters, right? Because I got meters per second times seconds, I get meters. Minus 20 meters. What does that tell you in terms of a graph? And let's suppose T1 was that, and let's suppose the time interval from 1 to 2 was, say, 10 seconds. Well, it doesn't quite give you the graph because I don't know where to start. I can tell you that if the best I could do, so this won't be a complete position time graph. What does it tell me? It tells me that from x1 to x2, there should be, oops, I had a negative. So there should be a negative slope where this part, well, the slope is minus 20, would correspond to a change. This delta x is minus 20 meters, right? So the distance or the change from x2 to x1, I must have started at a what? I don't even know if it's more positive. It could be this. I could put these points down. I could put it down here. My graph would have the same orientation, and my delta x would still be minus 20 meters. Both of those satisfy the area under the graph. But I don't know where this is, right? I don't know if it started positive and ended up with a smaller positive number. I don't know if it started with a small negative number and ended up with a greater negative number. But I can tell you that my position changed by negative 20 meters. So that's the difference. Okay, and that's where we're at with chapter 3. You are familiar with the equation. You know that the equation can model this motion. You know that your velocity can be different over different time segments, but you know that for each time segment, the velocity is constant. Okay? And more importantly, you are now equipped with two kinds of graphs to describe motion, a position time graph and a velocity time graph. And with that, we're done with chapter 3.